Hello, and welcome to the session introducing an efficient design flow for IC power module design. My name is Nikola Kontic. Firstly, I'll just look at the power module market, the global value of it. And for the current analysis that is available in 2019, the global power electronics market was sized approximately 33.5 billion. Depending on how the analysis was done, it can be less, it can be more, but this is just one analysis of the market. And over the next 5-6 years, it's estimated to grow by about 4.7% up to, in some analysis, 6.5% and so forth. So we're into a growth in this power electronics market. Power electronics circuitry devices, they alter and control the electrical energy from the source to the load in an effective way. And our goals really is to improve the energy conservation in a variety of applications. Now, those cover, as most of us are aware, the automotive market. We're in a very agile and very dynamic area in this market sector, including electric vehicles and hybrid, with transportation covering aerospace, aircraft, trains, etc., is another area where power electronics is changing the environment for that market sector. Energy, as we move into renewables, and consumer and industrial market sectors also are focused on energy conservation. It's necessary to reduce the losses in power devices and realize energy savings for the reasons of reducing carbon dioxide emissions and the inclination towards more renewable power sources. If we just have a look at some of the companies that are involved in this area, so we can see various companies involved that are both in Asia and also across Europe and the Middle East. And within the other sectors, we would have companies such as Renesas, etc. So Infineon, onsemi, etc., ST Microelectronics in the European, Middle East space, and the Asian companies like Mitsubishi, Toshiba, Fuji, etc., being in Asia. So the spread is across the world. There's no one market that is dominating the top global market share area. Looking at some of the challenges and market driving factors, as we know, some of the milestones that we're faced with from the political and the environmental and social aspects are prohibiting the sales of the internal combustion engine. And we have legislation imposed upon many of our market areas where we need to change and evolve to using more electric vehicles in the market to reduce the emissions, the climate change, and the environmental impact. And those are the challenges from a general market, but the technology challenges are such things as how do we charge an electric vehicle more efficiently or faster? The driving factors here are a case of we don't want to be sitting for 30 minutes every 200 miles to charge an electric vehicle. We need to find more efficient and effective ways to get the transport moving. So from that point of view, electrical and electronic design elements are the high voltage silicon carbide use in power inverters, 1.5 volts, 800 to 1.2 kilovolts. The currents are very high. Other technological challenges are the battery capacity and the capabilities and the materials involved. And then also the module packaging. How do we deliver it in a package that is both safe, reliable, and sustainable for the future? The current or traditional design flow for power module design is one of physical containment. We have several semiconductor devices onto a printed circuit board. We have the devices are soldered or sintered onto a substrate, provide electrical and thermal contact and electrical insulation. And also, compared with other discrete, we carefully design the chassis, the housing of these power packages, because traditionally they have a high power density and need to be much more reliable, and they are as a result. So typical design flow is one of having mechanical CAD driving this area of the design, where the mechanical CAD information is passed for structural analysis. So we don't have any electrical analysis possibilities. We have no electrical connectivity in here, but to give you an example, here we can see a particular device, and we can see some of the connectivity between the two different modules. And we can also see connectivity within the component. For example, we've got multiple diode bond wires from a diode. So the challenges faced here are the connectivity between different boards in a module, also the connectivity and the component connections within a component, and also how this interacts with the actual package itself. And what you can see on this image again is we can see some mounting areas, but also there are some mechanically designed connectivity points. So we have some terminal posts here on the left-hand side, and we have some signaling on the top here for defining that. And as I said, traditionally that is designed by the mechanical environment, although it has electrical significance in the design. So with CR8000 design environment, the proposed flow is one that is relatively new, where we can take the mechanical design information, which is, as I said, the chassis, the housing, the ports or the copper clips, and we can combine that with the electrical information that is captured through circuit design using CR8000 Design Gateway. So both with the mechanical and the electrical information, we can pass that on to the physical implementation of the design flow, which is done, the layout is done within CR8000 Design Force. And once we have that information and we start designing and we've implemented the product, we can then pass that on to structural analysis with mechanical design elements. But now we also have that electrical connectivity information, so we can send that out to electrical analysis. And as I said, we have that connectivity information, which is increasingly required for performing electrical analysis. The complex power modules we're designing need to perform a various electromagnetic analysis. So in terms of the functionality and the features that are required by users to implement power modules, some of the features available in CR8000 Design Force are the 3D bonding between the different devices, between the different multi-boards, the bonding between the mechanical elements of the design and the electrical power devices in the design, and also the bond wires. So traditionally, years ago, that was just a regular round bond wire, but these days we have bus bars, copper clips, we have ribbon bonding capabilities. So having those design elements to facilitate features in the design process is vital. Also, as you saw in the example, the multi-board design case, we need to characterize and capture the information, the features of bonding wires between multiple boards, and finally, some of the areas that are important, especially that were done in the traditional mechanical design element, was some 3D design review elements, or I'll refer to them here as 3D package design rule checks. So clearances, positioning of electrical connections in terms of the proximity to other elements around it. And once we have that electrical and mechanical information, then we can, of course, pass that to the electrical analysis tool. So we can export that to various electrical third-party analysis tools. But also we have the capability to then pass both to the mechanical design, the electrical connectivity, and also the mechanical information, and that's done traditionally using a stepped format. So in the demonstration, just to give you an idea, we have two IGBTs, we have some ports, which are gate 1 and gate 2 ports, and then we have the negative power and the positive power, and we have a couple of diodes involved. So how that will look with the design, we have the different mechanical design environment, designing the chassis, which in this image I have shown as a semi-transparent. In the other items performed by mechanical, we can see the terminal for the connections to the outside of this particular power module package, and we can see some of the gated signaling pins also. And then inside we can see how we're going to define that. So moving on, as I'm showing here in the demonstration, we have a package tab on the ribbon in Design Force where all the features for packaging is available. And firstly, we want to show how we can bring in some of the mechanical objects. So we're going to enable the visualization of accurate parts, which we can see the mechanical information come through. We've got the chassis, which is semi-transparent. And when we come to do design work, it's probably that we typically turn that off and we can start doing the design work. So you can see here we have the two modules, two IGBTs and the diodes. And so the different wire bond connectivity, so in component connectivity, and then finally to the gated two signals at the top. So in the functionality on the package, we're able to add wire bonds, delete wire bond pads, move them. In this case, we'll add a single bond wire with inside this particular IGBT. So we're picking on the pad and we're defining the starting point for the bond wire, and we'll define the end point of the wire. So it's starting at this point, moving up along the pad, and then we can connect to the next pad within inside of this component. And we can continue that through the different pads in this particular component and finally conclude. And now if we toggle into the 3D view, we can see the profile of the bond wire, although it's a very thin line at the moment. We're just seeing how it's going to appear based on the profile. And with inside the package rule editor, we're characterizing how that will be visualized and how that will be manufactured. So here we can change the bond wire diameter to visualize the actual bond wire as it's going to be manufactured. Again, having a true digital twin as to what will be manufactured. With inside the package rule editor, you can also see the profile where we define how the bond wire geometry is to be defined, visualized and created. So we specify the height of the bond wire above the die pad. the angle at which it exits the die pad, and then onto a bond pad or another die pad, the angle again, and the distance. So we can characterize fully each of the bond wires, the geometry of it, and then visually see that on the particular design. We can change it dynamically. So as you can see here, changing the 60 to a 50 degree angle, we can see the change in the bond wire. So it's very helpful. This would have traditionally been done again in the mechanical to see, okay, maybe that bond wire isn't ideal. And in this case, we can see here the discontinuity in the bond wire. So this may be something that the manufacturer may have spotted and will rectify, but now we can do that to make sure the design is correct by construction. So moving the attach point to make sure that it's coincident. And now if we toggle back into 3D, we can see that this is a continual bond wire, fully characterized as one bond wire. Now taking an example of connecting, defining a bond wire from the component to a mechanical terminal, to a mechanical port. So if we add a particular bond wire from this gate 1 port, which was defined by the mechanical design environment, we can then connect that into the component, and we can then visualize also that bond wire. Now we can see again, having the value of 3D visualization, we can see that maybe that attach point is not ideal. So at any point in the design process, we can move those attach points. So in this case, again, using the ribbon, there is a move function to move the drag the attach point to a more suitable location. So visually, we can recognize that that's a good connection point. Now, when it comes to connecting between the two power modules, we need to perform a bond wire, but this time it's going to be a ring connection. So we can specify the pad type being ring and then start the connectivity from one board to another. Now, in this case, I'll just show you some examples where we have the online design rule checking for the design, where maybe the attach point is too close to one of the other design elements. And online DRC will immediately flag up that our clearance is an issue. So if we check to highlight what is the issue, we can see that the spacing between the attach point of the bond wire is 0.09, and we need a clearance of 0.2. So immediately we can resolve that. Again, this was only caught in the MCAD design review phases, but now we can do that inside of the design implementation stage. We can also perform that with DRC check at a given time. So as an example, if we add an additional bond wire, but this time the 3D clearance space, I'm going to just change to have a bond wire coming very close in the 3D view. So in a 2D view, we may not see the issue, but if we add a single or a ring bond over onto the pad, and now view that in 3D space, we can see that actually the bond wires are coming very close to one another. So we can perform a DRC check at this point. So inside of the ribbon, we have our package design rule checks. And inside there is a multitude of different checks. So we can see that there is several checks. And I'm specifically interested in the bond wire 3D check. So I can turn all the others off in this case and focus on to see that the 3D bond wire clearance needs to be 0.05, for example. And now if I perform the check either on the entire board or a selected area or a selected point, we can see visually in the 3D view, we can see the error flagged up and reported, so we can take mitigating action to clear that, which is again moving the attach point of the bond wire to something that will avoid the check. And if we perform the check again, the clearance is sufficient, so we don't have a design rule check error. So once we have completed this area, we have the information ready for the electrical analysis, and this information can then be passed out to the electrical analysis. So on the analysis tab of the ribbon, we have different simulation tools, and we can export, in this case, to ANSYS, the information, and you can output specific signals, or you can decide to output the entire design and various factors for parameters for the simulation. Just moving back to how we share the information with mechanical CAD, we have the step output available. And again, that information will go forward into the mechanical for performing those checks. So how have we verified or worked in developing this more efficient design process? Well, we've typically, as our Zuken tagline, the partner for success, we work with our partners and developed a more efficient design process for those partners involved. In this case, the user case study we developed was to have the particular parts in the design, capturing the schematics, performing the implementation, and finally moving on to analysis. But the important aspects here are the characterization of a ribbon bond and also using copper clips or bus bars, being able to visualize them inside of the physical implementation tool, the package design module tool, and also passing that information electrically to the analysis tool. You can see here some examples where the mechanical design environment created the bus bar in a certain shape to avoid some of the ribbons that are passing underneath. So of course, in the physical implementation in Design Force, we have those 3D clearance checks to make sure that the ribbon bond is sufficiently away from this mechanical bus bar that is connecting across. We have imported the bus bar from the mechanical. It's come through as a step model, but we have the electrical information for the connectivity of that particular item. We have the 3D checks, and also we have the characterizations of those ribbon bonds. Now, traditionally, years ago, we would have done that with 3 bond wires connecting the same point, but the technology is there to generate these different ribbon bonds. And when I say ribbon bonds, we can characterize them in various ways for the design. We specify on a traditional bond wire the diameter, but on the ribbon bonds, we have the width and the thickness to define. So we can see for the diode 1, 2, we have particular ribbon geometries, but on the third one, we need a much thicker ribbon connecting it. So we assign the different types and profiles as we did with the bond wires, but in this case for a ribbon. And we can see here how the information is characterized in the system. So for bond wires or for ribbon bonding. And then we have the profile of the ribbon. Again, the ribbon is different profile geometry compared to a bond wire. So in summary, I've shown you about reducing the design time and increasing the quality through the use of ribbon bonding in addition to the conventional bond wires. The complete and consistent data that we can now pass, both the mechanical information and the electrical information to analysis. Improving the efficiency in the design process. Well, the information is now both the mechanical information and the electrical information is in the design implementation tool. So we can perform some of the 3D checks early in the design process, and we can deliver a much more correct first step design. This enables us to have a quick, efficient, and productive design flow. And from the virtual or the digital twin, we can actually visualize and have a more accurate view of the product that we're designing. So enabling that digital transformation and the digital twin design environment, design process that we all seek, while being able to output accurate information for the different analysis and design reviews, be them through mechanical or through electrical analysis. And that has concluded my presentation. My name is Nikola Kontic, and my contact details are available. Thank you very much for attending today.